Hello, everyone. Thank you again for the second day of our workshop, Hands-on Machine Learning with Python. Dr. Abdolghader will be with us in seconds, and then we can continue. And if you have any questions from yesterday, could you just put that in the comment, and we try to address it maybe before starting the new concepts.
Okay, so hi everyone. Let's start the second session. In this session, we are going to implement and learn about two machine learning algorithms, which both of them are unsupervised way. So just as a quick review, in unsupervised learning, the model, by seeing many examples in data set, attempts to learn shared features among the examples. So it makes a kind of feature probability distribution. Data clustering in data analysis approach, which group objects have similar features. A common unsupervised clustering algorithm is k-mean clustering, and also principal component analysis, which here we are going to cover both of them, k-mean algorithm and PCA, or principal component analysis. So you can see the k-mean clustering here in the figure below. We do have 20 data points or 20 examples. We are trying to apply an unsupervised learning algorithm to classify all these 20 points to three classes, which you can see here by red, blue, and green. And the difference, for just recalling you, between supervised one is that here we never label our data set. It means that we are just feeding the model by some raw data without labeling them, without, for example, let me use my pen. For example, computer or the model have no idea about what this data point is. So this is unsupervised. So first, let's start with the PC, or principal component analysis. So mostly large data sets, in the real world, are becoming more frequent in many fields, and we can and there is a challenge to interpret them. So PCA is a statistical techniques that find dependencies between the dataset variables, and then reduces the dataset variable dimensions to a few that contain the most information. For example, if you look at this example below, our dataset depends on three variables, variable number 1, 2, and 3. But by applying principal component analysis, or PCA, we are able to represent this dataset in a new representation, but this time with just two variables, which we call them first principal component and second principal component. And always the first principal component means that the data has more variance to the first principal component. It means that the first principal component contains more information about our data set. And then the second principal component contains more information. You can imagine that we have a data set that has 200 dimensions. First of all, we can never plot a data set which has 200 variables, because it's not plottable. And also, all of those dimensions are not really necessary. So usually we apply some dimension reduction techniques, which one of the most powerful one is PCA. So we can shrink the data set variables or dimensions from, let's say, 20 or 200 to just 2 or 3 dimensions, and almost keeping all the necessary information about the data set. But how it works? So you can see when you have a data set, the original data set, you can find some relevant features, which these features are those that we are looking for, keep them. These features contain most valuable information about our data set. We do have some redundant features, which it means that some just zero data, which is not necessary at all to keeping them. And also we do have noise. You can imagine that, I don't know, you are working with a hyperspectral image, then you're recording some noise, you are recording some zeros, and also some, some not relevant information. But you also recording some useful information. So then by applying a PCA, which basically is a linear transformation, we can represent our data set based on new principal access or new variables. So there are 5 steps we need to implement to apply PCA. First, we need to normalize the data set. It means that sending it, having it between 0 to 1. So with the way that we just discussed yesterday, then we have to make covariance matrix and compute that. What covariance matrix is, in the next slide, I will tell you. Then we should solve eigenvalue and eigenvector problem, which gives you the principal component or eigenvalues and eigenvectors. Those eigenvectors are uh, new basis for representing our data set. And then we need to rebuild the feature vector based on the new principal access or new variables, and then recast the data along the principal components axis. So if you see here, there are steps. So normalization, it means that the value of every single data needs to be subtracted from the mean value, then divided by a standard deviation. And about the covariance matrix, when we are talking about variance, it means that we are calculating the divergence of all data set respect to the mean value. So it tells us how much far our data set respect to our mean value. But imagine that if you have uh, 2 variables, like that, if your data set depends on X and Y, then you cannot calculate the variance. Instead, there is a new definition in statistics, which is called covariance. So basically, covariance between variable X and Y defined like as this. Xi minus mean value of data in the X dimension multiplied by Yi. It means that example, the variable of example Y minus by mean value of the Y divided by number of examples minus 1. Now just imagine that instead of this one, we replace it with the X. Then this turns to the variance, which basically just X minus X bar multiplied by, again, X minus X bar divided by n minus 1. So basically, this is just a definition of variance, which is mean square error of the data respect to its mean value. So what a covariance matrix gives us, it basically gives us how 2 different variables are dependent of each other. So, but how we can make this matrix is like this one. Just imagine that you have 2 variables. So for making covariance matrix, we need to do this. The covariance between X and X, covariance between X and Y, X and Z. Now I imagine that I do have 3 variables. So then making this matrix and finding the eigenvalue and eigenstate of this matrix. So it is all for PCA we need to do. So now we can go to the Google Colab.
If we have like 100 dimension data or 100 variables, then this matrix would be like 100 by 100, right? Giant matrix.
Yeah, then the matrix would be 100 by 100.
Okay. Okay. So it would be very computational expensive, kind of, right?
It would be really computation expensive. But there are some methods which is called vectorization. Then the computation would be so easy.
Like,
Can we go to the Jupyter Notebook or Google Colab.
Yeah, I guess, I think.
And I send you the code.
Okay. You send me, or you can share it directly there?
I will share it on my computer, but before I will send it to you.
Okay, when you saving that, maybe save as that IP, and because the other time people had some problem opening that.
So I can Telegram it to you.
Okay. Last time it was in PY format, and I think some people had a little bit problem with it opening.
Okay, now you have it.
Oh, okay.
So whenever you are ready, I mean, everyone has the codes, then we can start.
Yeah, I just. Okay. Yeah, everyone just check the chat and then you can download it. Should be no problem opening it by the way with the Google Colab now. Okay, now should be fine. Can start, I guess. Yeah, I sent the guides. I think now we can start. I should have it now.
And you can see my screen, right?
Yeah.
Okay, so first things first, so we need to first import the libraries. So now we are going to introduce a new library which is called pandas. This one. This one is usually used for data analysis. So we importing pandas as PD. So it means that whenever we call PD, it uses pandas. Then the NumPy, which I introduced it in the previous session, which is for computational. It's a computational library in Python. And then sklearn, which is also for data analysis. and this one also for decomposition, and matplotlib, which is for plotting. So these two basically, I mean, the third one, this one is doing normalization for us, and this one is going to finding the eigenvalue and eigenfunctions. So I mean, this one refers to your question. So I mean, people have already written some codes which is really efficient and fast. So by using this decomposition, you can find eigenvalue or eigenvectors of matrix with huge dimension. So the second things we need to do, we need to import the data set. So I picked this data set. I mean, this is on web. So let's first run this one. When I see the green tick here, it means that, I mean, this implemented well. So then I need to download the data set here. So it is done. Then, I mean, this DF means a data frame. We are going to create a data frame. What data frame is? Data frame is something like spreadsheet in Excel. So we will see later. So the, the syntax for that is PD, I mean, which we introduce here. We are importing NumPy, pandas as PD. So PD dot read CVS, and here the first argument refers to the web address, and the second one is the name of the label. So here we made the spreadsheet or data frame. Now by this this comment df.shape, actually .shape is a command in Python which gives you the dimension of your matrix. So it tells me that I do have 150 rows and 5 columns. So it means that 150 examples with 5 columns. And if I want to see how my data set looks like, I need to just df, I mean printed df, I mean just type df and shift enter. So now you can see it's like Excel spreadsheet or data frame. So the first column here refers to the index, and in Python it always starts with 0, 0, 1, 2, 3 to 149, and this one the labels at the top, sepal length, width, and width. These four are 4 dimensions or 4 variables of my data set. It means that every single example depends on these 4 variables. So, and you can see their values 1, 2, 3, 4, and we do have a target or y. I mean, this is called the y. It means that if I give my function the values of 5.1, 3.5, 1.4, or 0.2, if I give these 4 features, it gives me the INRS-EMT or something. And here we do have 3 categories, 3 data sets. So, but for this one, if you want to plot this data set, is impossible because the most that the highest dimension we can have for plotting something is 3 dimensions. But here we do have 4 dimensions. So now it's better here to apply some dimension reduction algorithm like as PCA. So
is it some type of flower? Or...
I think it is. Maybe we can take a look at this. So maybe just.
Oh, okay. No, it's fine. Yeah, just.
Well, you can see it quickly. I forgot actually what it is. Yes, it's kind of flowers. Okay. Right. So and here we need now to define the features, and the features that we discussed was these 4, this one, this one, this one, and this one. So these 4 are the feature label. So we define it as here as a list. We are using a Python list. So features equal to the list of this. So, and we put every single label in a quotation. So sepal length, sepal width, petal length, and petal width. So again, shift and enter. If I'm going fast, you can stop me. Then we need to now just make a feature matrix. I mean, we need to get rid of the labels and just have the numbers, have the features alone, I mean, without the labels. So this syntax, df, which is data frame, dot loc in the bracket, then these two dots means that all of them, so all the columns, and the feature refers to the raw dot value. So this syntax basically copy all the features value to the matrix X. So, and if I want to print the shape and see the size of it, you can see this is the shape 150 and 4. The previous one, which we did that, I mean here, it was 150 and 5, which this one, the one extra refers to the index. I mean, this one was referred to this one, 0, 1, 2, 3. But for the X matrix, we are just trying to keep the values of the features. I mean, we are trying to keep these four and just the values. And you can see here is the list. 5.1, 3.5, 1.4, and 0.2, which is exactly 5.1, 3.5, 1.4, and 0.2. So here we made our feature matrix, which looks like this. So now we need to also separate the y value, the target value. Again, we are using the same syntax. I mean, I'm just copying it here to just show you the difference. So you can see for the X, it was equal to df data frame dot loc, all the features and features column dot value. And here is again the same. Y equals to df data frame dot loc. This double dot means everything. And the target, which means that the column of target, dot values, which means that just keep the values, not the label.
So it will assign some values to each of those groups, right? To each of those flower, it will assign one number or something, right?
After the PCA, it does.
Oh, okay.
For now, we are just trying to make two matrices. We are just trying to make from here to here. I mean, from here, the sepal length to the petal width.
Yeah.
We are going to just make this matrix as a X because this is our variables. And the target is our output. So we are also to use to save the output in a separate matrix, in a separate column matrix, and the feature in a separate matrix again. So yeah, and the shape of Y is exactly what we were looking. It's 150 and 1. It means that just we have one column and no row, because I mean it's just a label of Y. So the first step, which we discussed in the slides, was normalization. So we need to subtract the value to their mean value and then divide it by the standard deviation. So here it is. I mean, we do not need to use the for loops, or I mean, we do not need to use loops, which takes really time. So now, as I told you, the pandas is a powerful library. So there is a syntax or comment for it. A standard scalar dot fit transform x. So just this single line do all those for loops. So that's all, it finished. So for just my curiosity, I'm going to check the x shape to see if it doesn't change. And again, you see that, I mean, the shape is the same. So, and the last step, I'm going to define the PCA function. We called it as a PCA equals to PCA capital, because this PCA, we basically downloaded that. I mean, here, we import it. Dot decomposition, import PCA. So we have this function ready in our computer. So here I just defined it as a PCA equals to PCA, and the argument of this function needs to give number of components, number of principal access I'm going to have. So I'm going to have two components. I decided to shrink the dimension of my data set from 4 to 2. So here I defined that my PCA function would apply to two principal components. So n components equals to 2. So it is defined. Then principal components equals to the PCA which I defined here, PCA dot fit transform dot x, which x was our feature vector. So as simple as this one, I mean, everything's done. Now,
The number of components we can choose arbitrary, or we need
it's
to choose.
arbitrary, but couldn't be more than your original data set because
Okay.
you're shrinking actually.
So if
You
we,
can,
okay, maybe later if we come back and at the end maybe one time we try with one.
yeah,
and
we can
see
try.
what happens. Yeah.
I can imagine that if you try with one, it would be one access and all data would be allowing the access, but we can try to see how
Okay. Then yeah, then it doesn't work actually.
we can try it. But so then now here we need to define principal access. So again, PD dot data frame and data equals to principal components, which here we define them. So, and the column name, which we say that P1, which refers to principal component number 1, and P2 principal component number 2. So let's add these to here. And now the shape of principal component would be 150 and 2. It means that we have a feature vector that has 150 examples that depends on just two variables, because here we defined our principal component has to be 2. So, and if we want to take a look at here, we can see here. So the first example, the principal component 1 has this value. The second example has the principal component of this one. So you can imagine that we had X, Y, Z, and T. Now we shrink it to just X and Y. I mean, the different X prime and Y prime. So now all those are 150 examples depend on just two variables instead of 4, which we call them, label them as principal 1 and principal 2. So now we are going to add them to the real metrics for just representation and the target one, because all those examples was referring to a target, right? So, oh, sorry. So it's here. So the first example that has a principal component value equals to minus 2.2 and something, and principal component to 0.5 is in the group of IRIS-Setosa. So the second example with principal component 1 and principal component 2 belongs to this group. And if you just compare this one, now remember, the first one, I mean, the 0 index was Iris, Setosa, and the second one was again, I mean, the first 4 belongs to this group. Now we can check to the real data to see if it is true or not. So you can see, I mean, the first 5 belongs to the same group. So this means that although we shrink the variables of our data set, I mean, the variables that our data set depends on them, again, we can refer them to their classes. So nothing changed. I mean, it means that even now we having less dimensions, but our classification is again working. I mean, we just only have 2 numbers. We can tell that example number 1 belongs to this group. Example number 2 belongs to this group. But previously, we needed to have 4 variables. But now, I mean, we get rid of some not useful information and just kept some useful information about data set, which was here too. We again can have, I mean, this classification. And for just plotting purposes, I'm using the PLT function, I mean, which I wrote it here, but for practice, you can also do it yourself. So you can see principal component 1. Even I can have now a visual a visual view of our data, because previously I had 4 dimensions, which is not possible to plot, but now I do have 2 dimensions, which is plottable. So you can see the first group has principal component 1 between -3 to -2 and -3 to 3 to +3. The second group, which is green, has a principal component 1 from -0.5, let's say here, to 1 point something, and the principal component 2 is from maybe close to -3 to here, close to +1, and the third group here. So it is also a way of classifying the data, because now we know that the first group just depends on 2 parameters, and when these 2 parameters are within this range, for example, for the red one, when the first parameter or first principal component is within -3 and -2, and the principal component 2 is within -3 and +3, then all the data points in this region belongs to the red group. So this is also a way of classification. So maybe you can, yeah, we finish this one, but I suggest maybe you guys can also run the codes by yourself to see how this is working, if you haven't done yet.
If we
So we can
in
change
the
it. Yeah.
in the data that we import at the beginning, it
Yeah.
looked like actually it was already in different. I mean, it wasn't like random. I mean, the initial data that we imported, it already looks like they were separated already. I mean, like the
Oh.
first one looks like Satosa, and then
Let me see, going to the other one.
does it make looks like it's already separated. I mean, like
But it's fine, because
classified.
you know why? Because the goal of algorithm was not classification, it was dimension reduction. For
Oh,
example,
yeah, you're right. Yeah.
instead of 4 parameters for representing a group, now we are using 2 parameters for represent a group. Actually, the goal was this one.
Okay, yeah. So then we can give this guy, for example, to another, script or something to classify.
Hossein has a question. How did you make the principal data? You mean the principal component, right? Correct. Oh, okay. Maybe I jump to this one, I can get back. So here in the first step is just normalization, right? And second, all the process that you have seen here, I mean this one, PCA equals to PCA number of component equals to, and then fit that principal component, everything is happening in just 2 single line of code. So what here is happening, let me show you the slide. So it's here, because I'm using some pre-written library. I'm using the pandas library, or it was pandas library. So what those 2 lines are doing, those 2 lines are making this matrix, which is called covariance matrix. And what does covariance matrix means? Covariance matrix means that it finds the relation between variables, and then in that single line of code, it starts to computing eigenvalue and eigenfunction of this one. So then it starts to sorting the eigenvalues based on the bigger one to the smaller one, from the bigger one to the smaller one. So we said to the computer, we need just 2 principal components. So the first principal component is the biggest eigenvalue of this matrix. The second principal component is the next biggest value of the eigenvalues of this matrix. So this problem is actually just eigenvector or eigenvalue problem solving. I mean, if you have background in mathematics, I mean, we can represent a matrix based on some vectors. It's like that. I can represent a point with three numbers in x, y, and z. And in linear algebra, I can also represent a vector, or I can represent any object with some basis. Like as here, I can represent a matrix by just expanding that matrix to some components and some value. So basically here, those two small lines of code just compute the principal component and just compute the eigenvalue and eigenvector. So then start to sort the eigenvalues from the biggest one to the smallest one. Then by telling the computer that I'm just interested to the two eigenvalues, then it picks the two biggest eigenvalue, because I mean the biggest eigenvalue means that that eigenvector or that base is more important than the other. So this is actually the basic of what was happening in the code. You're fine with the answer? Thanks. So you're welcome. One of the interesting thing which I was telling before starting the session was that, I mean, usually since in machine learning or data science, many libraries developed. I mean, actually, if you don't use for loop or something like that, it means that you're a professional coder, because using a for means just spending a lot of memory on your computer. I mean, I'm also using the for loop, but there are many ways with people develop that. For example, just using the libraries, using the share file. I mean, this is one of the amazing features of the Python. You can use the really advanced libraries and doing, I don't know, 1,000 line of code in just one single line. When it becomes clear, when we are going to train a neural net, for example, a neural net, we can have a million layer. So just imagine that if you want to write optimization for a million layer of neural net, it means that you should spend maybe thousands or million line of code for just doing that. And one single mistake in those codes end up not running your code. So that's why, I mean, people just using some fancy things in programming, and they exist and they're free actually. So like as PyTorch or TensorFlow or Cross, they're all platform of machine learning, which you can find, I mean, as easy as this one. I mean, here for me was also amazing that how just with here, just with 2 lines of code, I can implement 10 lines of code, because this is already written. I mean, it's trustable. It is open source. Sometimes you can find some flaws, some mistakes in there, but if that happens, it means that the level of your programming is a way professional, that you see that problem. So I don't think that, for example, for me, after 10 years, even I can find a mistake in those codes. So that's why I usually trust to the libraries. And the good things that they are free. It's not like MATLAB that you need to pay for toolbox. You can just import them on your computer. So maybe we can go to the second algorithm, which is a bit complicated than this one. Shall we?
I think, yeah, I don't see any other questions. I think it was clear. So yeah, can go to the next one.
Okay.
I tried actually now to put it at 1, and yeah, it kind of worked actually to make just one component.
It worked?
Yeah, yeah.
Did you plot that?
No, I didn't plot it, but it,
when you did it, you can also share it for us, because I'm also curious to see.
I closed it.
Okay.
I didn't plot it, but to the last part it went actually. Just
maybe you might see an error because I was plotting for 2 variables.
Yeah, it decreased it, I guess, but yeah. If you have any questions, just drop it in the chat, and otherwise we continue with the next part.
Okay,
We
so
can continue. Yeah.
sure. The second algorithm which we're going to discuss is k-mean clustering. This algorithm basically is just for clustering. So I'm directly go to just explain the algorithm. And mostly we don't need to prove mathematically, why that algorithm is working, because it's we don't need that. When it's working, so there is no need for go on, because mathematically, if you want to prove this one, it would be 3 or 4 pages of mathematics and algebra. So I have done it once when I was studying, but then I was kind of confident that this is true, it's working. So first, for k-mean clustering, we need to specify the number of cluster we are assigning. For example, imagine that you have 2,000 data points, 2,000 examples of the data, and each example can depend on, let's say, 10 variables. So I can imagine this problem as I do have 2,000 examples. Every single example depends on 10 variables. So now you can imagine plotting even a single one is not possible. So then k-mean clustering is also a kind of dimension reduction. So, and also it uses for clustering. So first we need to just pick a number. We can say, I'm going to make those 2,000 samples in 3 groups. But also there is an efficient way of determining number of the groups. But usually people, from the previous background, they know that. For example, let's say I'm doing Raman microscopy or I'm doing microscopy. I know in my images I would see 3 species, or I would see 3 Raman spectrum. So then from my previous background, I already knew that I need to classify this data set to 3 groups. So then I select k equals to 3. But for some cases that, we have no idea about how many clusters we need to put. Again, there are some sophisticated algorithm, which is really behind the scope of here. So let's just imagine that we already know how many groups we are going to divide our data set to them. So second, we randomly initialize the k, and and the cluster, it is called centroid. So because it is the center of the group, so we initialize them randomly. For example, I will show you an example. Let's see here. So here, I imagine that I have 1, 2, 3, 4, 5, 6, 7, let's say 20. I do have 20 samples, 20 examples, that each example, let me pick my red pen. So each example here depends on 2 variables, x2 and x1. So now I'm going to group these 20 examples to 3 groups. I'm going to tell that, this belongs to this one, this belongs to this one, and this belongs to this one. For now, for just simplicity, I make this kind of, it is obvious by just, seeing that. But for some cases, it's not really obvious. This is for just, educational purposes. So the first thing I need to say that, look at the A. I just randomly initialize one centroid. So I told my computer that here is the center of my first group, here is the center of my second group, and here is the center of my third group. Just randomly initializing. Just pick a random number. So then what? The second step is here. We need to repeat, this is now the one iteration. This is the iteration, this is a loop of algorithm. So this one, I need to keep continue this one until I get to the good result. So which is called expectation and maximization. So the first step, we need to assign each point to its closest centroid. And the second, we need to compute the new centroid mean of each cluster. And continue this one until the position of centroid doesn't change. So now, I mean, I guess it's better to show it on the picture. So in the first step, I just randomly initialize 3 centers. I mean, I told my computer that this point, randomly, this point, and this point are centroid of my 3 clusters. Then at the second step, I'm going to compute the distance from all the points. I mean, when I'm saying all the points, it means that all these points except the centers. I'm going to calculate the distance, for example, of this one to here, this one to here, and this one to here. Again, I will do this process, same for another example. This one to here, this one to here, and this one to here. I will do this for all the data points. So, but let me clean this one. So just have one of them. So for example, I calculate the distance between this one, and this one. And my calculation tells me that, for example, this point here, this sample here is more close to the red, to the centroid red, number 2 centroid, right? I just label them as red. So I said that this belongs to this cluster. And this point here, for example, my calculation is telling me that this is more close to the blue one rather than the green or red. So then I assign this one to the blue cluster. So when I did this one, I kind of, I mean, let me clear this again. So by doing that, I'm kind of assigning every single sample to a centroid. So I'm just telling that these data are belong to this group or centroid. This one is belong to this. Oh, actually, and this one, I missed this. I mean, this is also close to this one. So this means that this is close to the red star rather than the green star. And this one belongs to this. Now, in the second step, I need to find a new centroid because obviously I can see that. I mean, this green star is not center of my cluster. So then I need to compute the mean value between the distance of all the points to the star. So after doing that, I shift or replace the centroid. I mean, from here, I'm changing to here. I mean, I move it to here because now this one is basically, I mean, if you just visually look at this picture, the center would be something here, right? So, and base of my calculation is based on mean square error, is based on the distance. I mean, just I'm doing x minus x1 square plus y minus y1 square, and then taking a square root. So then I move the centroid to here. I mean, here, I move it here. Again, I can visually see that, I mean, the best place for the centroid of the red group is here. So then after calculation, I will find the exact position of the red one. So I move it here again. And for the green one, I can see that also this could not be the centroid of the cluster. So something here has to be. Then after finding the distance between all the points, all the samples belong to this group, I move the centroid to here, as you can see here. So this is the second step. Again, another step is just I'm going to do this step again. I mean, repeating the step number B. Again, I'm going to calculate the distance of all data, all examples, respect to the all 3 centroids. Now I do have, it's like this step, you can see it, I randomly initialize the center. I give them some random position. Now I'm going to calculate the distance from here to here, from here to here, and from here to here. And again, for the second example, from here to here, from here to here, and from here to here. So, and it tells me that, for example, this blue line is much closer to the blue star rather than red star or green star. Then at the next step, I just tell that, I mean, this belongs to the blue cluster. Now I assign that to this one. And assign the closest one to this one, and assign this one to this one. So this has to be done in the low number of iteration, but I mean, in some complicated example, these iterations can happen over, I mean, 1,000 try. So I guess you understood the main algorithm, right? So you basically you first initialize some random centroid, find the closest example to the centroid, and then assign it to that centroid. Again, you calculate the distance of that group, all the examples in that group respect to the centroid, and shift your centroid. Then again, get back to the first step. I mean, just calculating the distance between all data set to the centroid.
Just one question. This one again looks like the gradient descent, the initial points is again looks like it's important. These random points that we select. Am I correct, or it's just
initial? Now let's imagine that instead of here, I mean the first I initialize that randomly, right? So now imagine that I put it here, the first one, second one I put it here, and third one I put it here, right? Then you can see this might become the first group, this one become the second group, and this one become the third group, right? But after doing some iterations, we mean the centroids would move. So yeah, initialization is important. I mean, if you do not do it randomly, for sure it helps your algorithm to converge faster. So yeah, and absolutely, some techniques exist. So instead of randomly initializing the center, you can do it in a clever way. For some complicated examples, yeah, there exists some techniques that you can initialize based on some previous knowledge, which makes the convergence of your algorithm much faster. Yeah, you're right.
okay? So, yeah, maybe. So there is a chance if I mean, they get clustered differently. I mean, right now they're very separated, but if they were slightly closer, or
yeah, if they are much closer, yeah, there is and actually you cannot do it with 100% accuracy. So people try to increase the accuracy of their model. For example, I don't know, you can do this one with 90% accuracy. You can this one do it with 70% accuracy. So it depends on complexity of your application. And absolutely, yeah, we cannot do it with. But for this one, I mean, we did it with accuracy of 100%. And because even visually, we can, I mean, group these data sets. We don't need computer.
okay, we have a question. What is the condition for stopping the iteration? Do we have any condition, or we just select randomly?
Yeah, there's a condition which in this type. Until the centroid position don't change. So for example here, if you again get back to this iteration and you see that this center doesn't change, because in the second step, I mean here, we are shifting the centroid. But if the centroid doesn't shift, I mean within a tolerance, let's say if it doesn't move within 0.0001% of its initial position, then we can tell the algorithm that stop the iteration. Yeah, and the condition is here. The second question. In your last example, the blue and green cluster are mixed together and seem to be complicated to define the center for them. Is this method available for all clusters? The last one, you mean this one, right? For
the flower example. Yeah.
We haven't plotted them. Oh,
yeah, I mean, just saying that if there were some overlap over there.
Oh, if there is an overlap between them, yeah, then the accuracy of your model decreases. Yeah, absolutely. I mean, it's not supposed to work for everything. I mean, it can work maybe, let's say, with 60% accuracy, but there's a threshold that people define. So if you are using this one for application that requires high accuracy, then this algorithm failed to work. Yeah, then you cannot use it. So It all depends on the application you are going to use that.
This K-mean clustering, does it depend on the number of dimension also? I mean, if we increase that,
No,
I mean,
you can use many dimensions. You can have many dimensions.
oh, okay. So
But
it's not just 2. If it has like 4 or 5 also, this
yeah,
method.
you can do it because I mean it's like the geodesic. I mean, let's imagine that you have a space with 5 dimensions. Then you can find the distance of every single point with respect to each other. Then the distance is defined as, let's say, the d defined as x minus plus 2, let's say the dimension n. I mean, it's just linear algebra problem, right?
Yeah. So there is no dimension restriction.
No, there's not, but then you cannot plot it. It's the only thing.
Ah,
And you don't need to plot them. You can say that, for example, imagine that you have a data or example with 10 dimensions, right? But at the end, you know that this belongs to which group. So that would be enough. Then you would tell that if I have, for example, the dimension number 1 has the value of, let's say, 0.2, number 2 has the value of 0.3, I mean, within a range. And dimension number n has the value of 0. Let's say something to something. Then all these interval belongs to group A. Yeah.
thank you. So I think we don't have any other question. Maybe you can go to the. You want to take a short break and then we continue?
Yeah, let's have a 5 minutes break.
Okay. Yeah, I shared the link down there. Everybody can get that and then can continue.
So can I start?
Yeah, I think we can continue.
Okay.
They should,
So
guys, they should have it. Yeah.
first things first, we need to import the library. So I'm going to use pandas, numpy, and matplots. First one is for dealing with data sets. Second one is for doing calculations, and third one is for plotting. So let's just download them. So here I'm going to generate some data set by using Panda. So df data frame equals to PD, I'm referring to Panda dot data frame. And when you are using data frame, you need to use dictionary. And when I'm telling dictionary, it means that something like this. So you would have label and the proper value. So this is the way you define the dictionary. You labeled here, you make a label, and this label contains the list here. I mean, it means that you can put a list in your dictionary. And the Y label has this list. So it's like maybe 20 or 10 data sets. So let's just run it. So now the first step is to randomly initialize the centroid. So no, so the reason that I use here as np.random.seed200, it means that because here, if I generate some randomly centroids, then in my program, I mean, here in my algorithm, I again going to call them. So this means that if the computer or if the Python creates some random data set, any time in my program, if I run the random, it used the same random before. So this line of code is just referring to that one. So k equals to 3. I decided to have 3 number of clusters. And here is just a simple loop for assigning the 3 different clusters randomly. So and np.random.randint, this means that generate random numbers, but in an integer way, not the float way. And the range is within 0 to 80. Again, for the y is within 0 to 80. So I made that one. So now let's plot the data set as well as the randomly initialized centroids. So here I'm using the PLT function, PLT library. So first I'm telling that I'm going to plot a figure that has the size of 8 to 8. Then I'm using the scatter method. And also the X would be data frame X and data frame Y, which here I defined the data frame. When I say that dfx, I mean, it takes all these values. When I'm saying that dfy, it takes all this value. So here, dfx, dfy, and the color is black and the size is 80. So, and also I'm defining a color map for my centroids. For the centroid number 1, I prefer to use red, number 2 green, and number 3 blue. Then by using these 4, I'm actually making the plot. And all these lines here is just for making the plot fancier. I mean, I define that the Y limit axis has to be between 0 to 80. The X limit axis has to be 0 to 80. And I define the tick parameter that has the length of 2.5 and width of 2.4 and the direction inside. So, and the Y tick and X tick has to be the font size of 16, and the Y label and X label has to be X2, X1 with the font size of 20, and finally PLT show. So here we go. These blue, red, and green are randomly initialized data set. Just give me a second to plug my laptop. So now, based on k-mean clustering, I'm going to cluster the black dots or black examples to 3 clusters here. So this is the assigning function. So here, what basically is that I'm using the for loop. I mean, here I couldn't find any pre-written library, so I'm just doing it by myself. So in Python, when you are defining function, you use def, name of function, argument of function. So df is a data frame which we had, x and y. I mean, this df contains x and y. I mean, the x and y position of our samples and the centroids, which we predefine them, randomly we initialize them. And for I in centroids dot key, which means that we are going to do this loop 3 times. Why 3 times? Because we do have 3 centroids. So we are going to calculate the distance from every single example to every centroid. So this has to be done 3 times. So, and here, as you can see, I mean, NP does SQRT. This means that it takes a square root mean. DFX minus centroid I, which I mean, I starts from 0. I mean, this for loop starts from 0, 1, and 2, because in Python, all indexes start from 0. So, and we do have 3 centroids, so the I would be within the range 0, 1, and 2. So centroid 0, 0 means that centroid first and the x component. This 0 refers to the x component. And again here, centroid 0 and 1 means that centroid 0 or the first centroid and the y component. So here basically I'm just calculating the distance between y component and x component of every single example from the centroid, and then just doing the power of 2. I mean, it's just a formula of the distance. So then in this line of the code, I'm going to just store them, save them in somewhere. So as you can see, this is our previous syntax or function, which just takes the value, all centroid, and add them to the column which access equals to 1. I mean, access equal to 0 in Python means the row, and access equal to 1, it means the columns. So, and finally return the df, I mean the data frame. So here we can see the result. So this 0 refers to the first example, second example, third, fourth, and 5. So the x value was 12, y value was 39. Distance from first centroid was, I mean, based on the calculation, was 26. Distance from second centroid was 56, and distance from third centroid was 56 and something. So you can see the closest one belongs to 1. So this one. So the closest one refers to the 1, and with the color of the red, which we define. This has to be done for all the samples, which I mean, we did it here. So the second, also we can see our result, as you can see, is based on the calculation. So every single point, the distance between every single point or every single sample was calculated respect to the randomly initialized centroid, and then we assign them a color. So now we can, in the first iteration, we have this group, I mean the blue group, red group, and green group. So, but obviously you can see the first iteration, we cannot always get the 100% accuracy. You can see this red is definitely belong to the green. But I mean, the first iteration, we can see this belongs to the red. So in the second iteration, this is going to be fixed. For the second one, we need to update the centroid's position. How? Just as I explained in the PowerPoint. Now I need to calculate the distance between all green points to the green star. Again, calculate the distance from all green points to the green stars and find the mean value. So obviously, the centroid or center of the green has to be somewhere like here, right? If you see my mouse. And the center of the red group has to be somewhere like here, middle of here. Now imagine that if you move this star to here, to this center, and if you move Let me pick a pen, like this is better.
We can see the mouse, it's fine.
Oh, it's fine, okay.
We can see
Okay.
the mouse, yeah.
If we move this one to here, and if we move this one to here, and also the red one to here, then after the second iteration, I can see that the distance between this red and this red becomes larger than distance from this red to this center. Then this red will turn to the green group, because previously the distance from this one to this one was closer than distance from this one to the red one, to the green one. But after the second iteration, if this green one moves to here and this red one moves to here, then I can see that, I mean, from here to here is much larger than from here to here. Then this red will turn to the green. So, I don't know how to get rid of this. Okay, so here it's just I did double. I shifted the centroids, and now let's plot the result. So you can see that it is just a result of shifting. So after updating a centroid, I didn't done the second step. So now the green star shifted to here, and the red star from here shifted to here. The green one from here shifted to here, and the blue one from here shifted to here. Now in the next step, I again need to do the assignment function, which is defined here. I mean, assignment function was defined here. It starts calculating the distance between every single point to the centroid. So in this step, I mean, here, the computer start to calculate, to calculate the distance from, from here to here, here to here, here to here, all data points respect to all centroids. Then it takes the minimum distance and assigned every single example to every single centroid, which we are going to do it here. Let's plot this one. So, you know how I can get rid of this? Or maybe erase out clear. Okay. So, oh, sorry. Then we need to continue. I mean, your previous questions, some of the question from one of the audience, that how long I mean, we need to do this iteration. We're gonna do this iteration. You can see we are using the while loop. While is true until the new centroid's position dot equal is equal to the previous centroid position. So then we run this one, and if you want to see the results, we can see now. I mean, this is actually, I mean, something that makes sense. I mean, this red is the center of all red points here. This blue is center of all blue points here. And this green is center of all green points here. So, yeah. Any question?
I don't see any question. In the, you said we need to define some like a small like within some range if it's changing.
Yeah.
Yeah.
We can define it as, I mean, being equal to the previous one, but we can also set a margin of error. So it depends on how accurate you want. But I mean, in this line, I guess it uses the equal term. So when 2 points become equal to the new centroid and the old centroid, when these two become equal, then the iteration stops. I mean, we break this while loop.
Okay. So if you want, we can set the margin over there instead of equal.
Okay. Margin, yeah.
Okay, I don't see any questions till now. For the for the, I mean, if we don't know the number of the clusters, and then we want to just see how many groups we have. The main idea would be similar to this one, right? The main thing.
There is a algorithm. It is called elbow method for clustering. So if you don't know how many clusters you have, you are applying elbow method. I mean, let me show you something better. Oh, it's here. So in elbow method, it's something really simple. It starts with different number of clusters, right? So first, it starts with one number of cluster. Then it calculates the error. So the error, if you use one cluster, would be something like, let's say, 2.5. If you use two clusters, your error would be 1.5. If you use three clusters, your error would be 0.5. If you use four, your error would be 0.4. So why it is called elbow? I mean, like this one. So it is that in the elbow point, whenever you get to this elbow point, it means that this is the proper number of your cluster. This is why it's called elbow method.
And how they define the error? I mean, how you define the error here? Is there any? Yeah.
You are just I don't know what that one. So you are just using the distance error. I mean, what we basically did here. I mean, like as this one, for example, here we didn't have good error. I mean, the accuracy was low here. So this is the way that elbow method is working.
I don't see anything. Okay. So we should be able to do this method also to do the previous example that you did at the beginning, right? The flowers.
Yeah, for sure you can do it. Maybe as a kind of, I don't know, take home practice. Yeah, you can do it. This looks not bad. So I can also share this one with you.
Yeah.
Oh, this needs signing. Maybe finding something free. But there are many things. If you just type elbow method and k-mean clustering, you can find different examples. So elbow method is really something good. It gives you at least a good approximation. But I mean, you do not necessarily need to pick the exact elbow point. You can go a little bit backward and forward. Maybe you can pick, maybe 4 is the best number. But I mean, your number is within this range. I mean, plus minus 2.
Okay. And yeah. We have other methods as well for this. I mean, I heard a lot they came in clustering, but are there other methods also that people use? Probably, I don't know, maybe less computational, demanding or.
Oh, for clustering.
Yeah.
Oh yeah, we do have we can use neural network for clustering, but you know what the point is. I mean, there exists many sophisticated algorithms, right? But usually people try to use the one that has the low cost of computation. So let me tell you something. If you know PCA, k-mean clustering, and regression, and maybe 2 more algorithms, you can find a job in bank. So decision tree is the 4th one. So by just knowing a few algorithms, because I mean, this is something routine. I mean, in all companies, in all financial and institute, people prefer to use something there is no risk on that. I mean, I have friends that working for Bank of Montreal. I can tell you that they just know, I mean, they have PhD in science and computer or something, right? But they forgot everything they have learned. They say that all the time we are using something regular. I mean, just maybe 5 or 6 algorithms. That's all, because it's working.
Yeah. Okay. So it will cover everything.
Yeah.
As much as it's enough. Okay. So yeah, I mean, I don't see any other questions. So, well, yeah. So for tomorrow, maybe guys, they can try the same k-mean clustering, this script, and try to do it maybe with the first example with the flowers. if they can. That's also more. It has more. Yeah, examples.
You have
more
nine
points.
let's say. So if you don't have any question, maybe we can end the session.
Yeah, so we can end the session really rather sooner. I don't see any questions. Maybe, yeah, if you had any question, maybe tomorrow. Yeah. Okay. Thank you, Dr. Abdolghader. Thank you, everybody, for joining us today. See you tomorrow at 5. Yeah, bye.